Algebra 2. Sorry. Operations, first and foremost, when you're adding, subtracting, multiplying, and dividing. That's going to be pretty straightforward because I'm just going to take the two functions and add them together. Subtract them, multiply them, divide them. What is a little bit more challenging is wrapping our head around what is the domain of our result. So we'll talk about that after we get all these done. So f of x plus g of x in order to add these, we need a what, Carolina? In order to add fractions in general, you need a close, common denominator. But GC, yeah, you're on the right track. So this particular denominator needs what? X minus 1. And this one needs x plus 2. So we will multiply out our numerators so that we can add them together. So that'll be x squared minus x plus x squared plus 2x all over. Don't multiply out your denominator. We only did our numerator so that we could combine like terms. So x squared plus x squared is 2x squared. And then 2x minus x is plus x. And the reason is because sometimes our numerator is factorable. Once you do all the combining, it factors out, and then it will also simplify with your denominator. This one is factorable, but if we take out an x, it's not like we're going to be able to cancel anything. Sometimes you will be able to factor the resulting numerator, and it will lead to more reduction. So either one of these is fine, but do get in the habit of looking to see whether or not your numerator can be factored in case there's more to be simplified. So there's just adding those functions together. You know what? With the subtraction, I'm going to kind of pick up here, but I'm just going to change this to a minus sign, right? Because I don't want to have to do that again. So it's going to be x squared minus x. The one thing to be careful of with subtraction, though, is that what are you distributing? A negative x, right? Not a positive x. So it's going to be a negative x squared minus a 2x all over x plus 2x plus x minus 1. So that's just going to be negative 3x over x plus 2, x minus 1. Multiplying fractions is easier because you don't need a common denominator. You multiply across your numerators, x squared, and then you multiply across your denominators, but again, I'm going to keep that as two separate factors. And then division can be tough. This is going to be a little bit tougher just because we're going to have a fraction divided by a fraction. But how do you handle that in math? Keep, change, flip, right? Good. So keep, change, flip. And actually, this will cancel. And you're left with x minus 1 over x plus 2. Okay, so does that make sense as far as adding, subtracting, multiplying, dividing? Okay. The domain part is harder. It's not as much physical work, but it's more thought. So in f plus g of x, actually the first three cases are all the same thought process. What is your domain of f of x alone? All real numbers except what? Right, so x can be anything but not negative 2. And what is your g of x? Right, anything but 1. So the domain of any of these first three when you're adding, subtracting, or multiplying is just going to be kind of the overlap. So this is all real numbers except -2. This is all real numbers except 1. So the domain for all three of these is going to be all real numbers except for you've got to exclude both of those. Okay? So wherever they intersect, essentially. So all real numbers. So think about this one, the f of x1 being a number line that includes everything but -2. And g of x can be anything but 1. So the intersection where things overlap is everywhere these overlap except for at -2 and except for at 1. So you have to exclude both of those from these three. If that makes sense. Okay. So for all three of these, I'm going to put domain is set of all x's such that x is a real number, but x cannot be -2 or 1. So D is going to be the same with one additional stipulation. What's that?
There's no 1 anymore.
No, you still, even though in the final version of it, 1 would be okay, it still at some point in the original would give you a problem. So you still can't have -2 and 1. But because we have a denominator here, like we're dividing by something, this whole expression can never equal what? 0, right? Because we can't have a fraction divided by 0. What x value would make this 0? What makes a fraction equal 0? When the... No, that makes it undefined.
Oh.
When the numerator equals 0. So if x was ever 0, it would be whatever divided by 0, which you can't do, because this whole fraction would zero out if x was 0. So this is the same domain, except we have one additional exclusion. So essentially, whatever's in the denominator, g of x cannot equal 0 either. And if you go back up and look at g of x, a 0 in the numerator is what's going to make that 0. So that division just has one additional stipulation. Okay? How about compositions? This is, I don't know where the other Algebra 2 teachers fall with this and how much they do it anymore. Yeah.
All our final answers will be x and
Whatever's excluded individually from these. And then you're...
never mind. I thought,
Okay. And then your division 1 usually will have just probably something extra. Did you, Alyssa, do you know what to do with this without me telling you anything? F of g of 2? Fake? Yes, meaning?
So you plug in 2 for G, and then
Right.
whatever that is, you plug in for F.
By backwards, she means right to left, exactly. So this notation with a little circle is the same as this. F of g of 2, there's two ways of writing that. But yes, you start with g of 2, plug it in. So g of 2 is going to be 2 over 2 minus 1, which is just going to be 2, right? That's kind of coincidental that that worked out the same. And then you do f of that. And then f of your resulting number, which coincidentally happened to also be 2. That's just not always going to happen that way. F of 2 is going to be 2 over 4. So a half. So f of g of 2 equals a half. Okie doke. G of f of negative 1, working right to left. You start with f of negative 1, which is what? Sarah, tell me what you get when you get it for f of negative 1. Good. Again, that's coincidental. And then g of negative 1. Laura? Negative 1 half. Good, because negative 1 over negative 1 minus 1. What'd you say? Positive 1 half. Sorry. I didn't catch that either until I did it out. Positive 1 half. And then f of g of x is just a little more annoying because you don't have a number to start with. So I can't figure out g of whatever number and get a new number. I literally have to take g of x, the entire function, and plug it into the f function. So g of x I just replaced with what it is, x over x minus 1. And I have to take that fraction and plug it in to the f function. Into how many places? 2, right? There's 2 x's, so that fraction has to get plugged in into 2 places. So, be organized about how you write this. X over x minus 1 is your entire numerator. And then within the denominator, you have another x over x minus 1 plus 2. And you have to clear complex fractions here. So what is the least common denominator of the mini denominators in there? It's just x minus 1, right? So I'm going to multiply the top by x minus 1 and the bottom by x minus 1. Top's easy because I'm not really distributing. It's only one term, and the x minus 1s will just cancel. Denominator, you have to distribute. X over x minus 1 times the x minus 1 is just going to be, good, x. And then multiply that by 2, and you might as well distribute your 2 while you're at it, plus 2x minus 2. So it ends up being like that. Now, we have to talk about the domain of compositions as well. Not so much these numerical ones where we were just evaluating, but we essentially just wrote a new function. Yes? Anything that is ever in a denominator constitutes an exclusion. Okay? So, even though down here in the very end, the only thing that's excluded, if you just were to look at this, like if this had been the original function, the only thing we would exclude would be what? 2/3. But this was not the original problem. This came from a process here. So if you look back in the problem, anything that was ever in a denominator, x minus 1, right, would exclude 1. And then also, and this may take a little more thought, this is a denominator, right? That cannot equal what? 0. Now that might take care of the 2/3, but I just want to check it. This cannot equal 0. So if I subtract 2 from both sides, x over x minus 1 cannot equal negative 2. And then how would you solve something like this? Or cross multiply. Yeah. So if I distribute negative 2x plus 2 cannot equal x, treat that like a 1. Oh yeah, that's going to take care of my 3/2. So that issue gets addressed anyway. So you might look at this, and this is the more interest. 2/3 obviously makes sense when you look at your final equation. But you might look and wonder why 1 can't work. if you try f of g of 1, let's see what happens. What's g of 1? There's your problem, right? You can't even get that process started. You can't do f of g of 1 because g of 1 is immediately undefined. So even though it doesn't lead to a problem there, you have to think about where this came from. Okie doke? Okay. Inverses. Tell me what you know about inverses. What main thoughts come to mind? Switch the x and the y. Absolutely. That is the bread and butter of the entire thing. Whether you're writing inverses or coming up with new points or whatever. Also remember your notation. I don't think this would have happened to you guys, but a couple years ago when we were looking at regencies, a lot of kids got an inverse question wrong. And we thought it wasn't because you didn't know how to do it, it's because you didn't know that notation well enough. Because the problem itself didn't say the word inverse. It just had that little f to the negative first power, and it looked like an exponent, but people didn't know that well enough. So I think we all tried to reinforce that more last year. So hopefully by now you know that that inverse notation is that little x superscript, I'll call it. So essentially interchange the domain and range. That's the switching of the x's and the y's. Reversing the ordered pair, all of that. Those are your key buzzwords for inverse. So 2, 3 becomes 3, 2. 4, 5 becomes 5, 4. 6, 9 becomes 9, 6. I wonder why there's no negatives in there. Just can do it. And then actually writing inverses, which I can immediately tell you this one's going to be your toughest. And we'll review something that we've done already this year when we get to it. But in the first couple, they're both linear. So we just switch the x's and the y's. And then get y all by itself. So step 1 here, Maggie, would be to do what to both sides? Yep. And then Mike, step 2. Right, which you can keep like this, or you can make it 1/3 x minus 5/3, whatever suits your fancy. Now this one I'm going to say we're done. On the next one, I'll talk about why we wouldn't be done at that point once we get there. So switch the x and the y. X equals 1/2 y plus 2. Subtract your 2 over. And then, Allie, how do I get rid of that 1/2? Yeah, but dividing by fractions is a little wrinkle. Multiply by 2. It's going to make your life easier. And because that's a binomial, just like we divided both terms by 3, we're going to multiply both terms by 2. So 2x minus 4 equals y. So we are not done on this one. And why not? It is factorable, but you don't have to factor it because this is the equation of a line. It's more of a notational thing. No? Yeah? Right. This notation used y, so we can leave it in y. This used the f of x notation, so we have to rewrite it as f inverse of x equals 2x minus 4. That's something that we have to take points off for on the regents. So you want to stay consistent with your notation. And then the last one's going to be the challenge, not because you have to switch the x and the y, but when you guys solve for y. Oh, maybe not even. No, don't divide by 2. Because you'd still have 1 over 3 plus y. A lot of people do that. They think if you divide by 2, then this side would just be 3 plus y. It's not. It's still 1 over 3 plus y if you do that. Right. You can cross multiply here. So if you cross multiply, distribute that x, you get 3x plus xy equals 2. You're solving for y, keep that in mind. So what's the first thing I should do from both sides from here, JR? Good. Subtract that 3x over, and next step, Andrew? Divide by x. You probably won't see this split up because it's not a number you're dividing by, it's a variable. And then again, notationally erase your y because this was in function form. Write it in function form. What's, you could. Maybe you would see that. It's still going to be a rational function, but yeah. Now, this doesn't talk about this, but what do you remember if I were to graph this line next to its inverse line? What would that look like? How would they... What is that? What does exact opposites look like on a graph? Not a 90-degree rotation, but there is a transformation I'm looking for. Right, it's reflected over that diagonal line y equals x. So that diagonal line y equals x should be a line of symmetry. Okay? Alright, your homework is 1s, 5s, and 7s. And then on the inverse section, I want you to do 1s, 3s, and 5s just because you're just going to do half of those. So I will leave this up here, and then when you get it, you can write down. Oh my gosh, your integrity things were fun. I love these. They make my Monday.
Mine was good.
You were just my inspiration, Alex.
Wait, why is it more?
What's that?
Why did you do that?
Well, this is what I'm handing you. I just want you to know that you're doing 1s, 5s, and 7s up there, and 1s, 3s, and 5s in the bottom right corner.